the information community, has participated, proposed many important experiments in the foundations of quantum mechanics and also in cryptography. He's also one of the founders of quantum for cryptography company. And we're gonna talk a bit about some new ideas about foundations of physics at all. I'd say not even quantum mechanics, no, I would say it's even more profound. And it's going to share with us these new ideas that are archived. You can look at them also, very interesting ones. And here's so I'd like to thank you, Nicolas, for your time to talk to us here.
Okay, thank you very much. Thank you, everyone, for being here. So indeed, this will not be a standard quantum information theory and even less quantum cryptography. It's a much more general and foundational topic that I like to talk about, which is really about the language that we, the physicists, talk. So these mathematical languages, several languages. So let me start immediately by motivations. So probably we all agree that one of our goals is to produce models of reality. And obviously these models should be as faithful as possible, which means, first of all, that these models should predict the correct empirical predictions, make correct empirical predictions. But there is a second aspect, which is not always stressed enough, which I believe is also equally important, namely that our models should allow us to tell stories about how nature does it. Now, we never start a lecture in physics just with equations. We need to tell a story. And examples of stories are, for instance, here for gravitation. Of course, we may start with Newton saying that, things tend to fall from the top to the bottom, but then we understand that actually things tend to fall towards the center of Earth, and that's why the kangaroos stick on Earth like we do. And also the moon orbits Earth because of the same gravitational force, a gravitational effect. We can then tell a lot of stories also about the tides, the moon that attracts the water in the ocean. And also if we go to more complex systems like this Brownian particle, let's suppose the red one is visible, the blue one are not visible, but we can explain what is going on by telling stories. The blue particles, the invisible ones, hit randomly the red one, and so that's the reason why we see this red one undergoing some Brownian motion. And we could also talk about the temperature of this blue gas, something like the average kinetic energy, how much they move. So even without equations, we can tell a lot. Now, if we go to our beloved physics, there is, of course, relativity and there is quantum mechanics. Of course, I'm more on the quantum side, but we all know that these other sides, relativity and cosmology, also exist. Now, in relativity, the picture that or the stories that we tell is something like everything is fixed since ever and forever. There's this block universe where the past is there, fixed, but the future is there also fixed, and there is this, a bit magical now, infinitely thin, that simply moves along the timeline and towards the future. The picture and the stories that we tell in quantum physics is very, very different. So typically we could have a light source that emits photons, obviously, with a beam splitter, and after the beam splitter, two detectors. We may name one 0 and the other one 1. And then we get a string of bits of 0 and 1s, which is random. So here in quantum mechanics, we would tell stories like new information gets created as time passes. And clearly these two are at tension, as we very well know. Einstein himself said things, or wrote actually, the following sentence. People like us who believe in physics know that the distinction between past, present, and future is only a stubbornly persistent illusion. So Einstein here was saying that this is just an illusion and that the reality is actually closer to this block universe picture. However, as a physicist, we know that we can do the following. At least as a quantum physicist, we know that very well. Let's suppose we have these two different parties, which we usually call Alice and Bob, but important is that they are at a certain distance. And let's make a few assumptions. The first assumption is that no instantaneous signaling or communication at a distance. Technically, we usually say just no signaling. And secondly, also, we have to assume no conspiracy in the sense that they exist independent variables. So for instance, you may imagine that there is a source of entangled photons, whatever, something here in the middle that sends particles to Alice and Bob. And this source should be independent of, let's say, an old Charlie Chaplin movie. We need that because in this way we can choose independent measurement settings or inputs here, X on Alice's side and Y on Bob's side. And of course, then if we do measurements, we get measurement outcomes, the results here. Now we make one more assumption, which is not really an assumption, just an experimental fact, which I write in this way, but never mind the way I write it. It just means we can violate some Bell inequality. This is a fancy way of saying we can violate the famous CHSH Bell inequality. And just with these assumptions and these facts, we get the following. And this is really a theorem, so this is not a matter of opinion or things like that. It is a theorem that says that the outcomes, so A on Alice and B on Bob, are truly random. So randomness really exists in quantum physics. Okay, here you have a proof of it by, okay, it's a Nature paper, so it has to be correct. But the argument is quite simple, and you can also read more about it in my book or in this review paper. And you can even quantify how much randomness comes out. So this is the probability of 3/4. And if you are larger than 3/4, then you get some randomness, maybe not full randomness, but you get some randomness out. So there is some randomness, some real entropy coming out. Okay, very nice. Maybe just a little bit about technology, because I find that also very fascinating. So this box is about 4 centimeters in size and contains all that. So the light source, the beam splitter, the single photon detectors, and actually engineers managed to put that even into this millimeter size chip. And once you have it at that level, with this very low power consumption, you can even put it into a smartphone. As you see, this is a Samsung smartphone. And so now you have really here the first mass application of quantum technologies, and it has really to do with this new information that gets created as time passes. And I hope that quantum technology will bring into people's mind the idea of scientific indeterminism. But okay, let's go back to more fundamental concepts. So motivations, already said. And now the main messages. Let me just start by maybe my conclusions by just telling you what are the take-home messages. There are 3 of them. The first one is the following: whether Newtonian classical mechanics is deterministic or not is not a scientific question. It really depends on the physical significance one associates with mathematical real numbers. Of course, I will spend the rest of the talk, or most of the rest of the talk, developing and explaining this conclusion. The second one is the following: the mathematical language we use when speaking physics has a huge influence on the worldview that physics presents to us. So obviously, all of you, I would imagine, speak Brazilian, Portuguese. Of course, you all also understand, probably speak English. And so you all understand, we all understand that the language we use make it more or less difficult to talk about some ideas or some concepts. And actually, it's the same with these different mathematical languages. Of course, again, we'll develop that in a few minutes. And at the end, my third main message is the following: we face a choice. Either our stories present events as the consequence of long past initial conditions, or else we understand the present as a result of indeterminate reality and the future is open. Okay, let's see how that goes. But maybe, I'm a physicist, okay, a quantum physicist. Why should I be talking about intuitionistic mathematics? Well, as I just said, to do physics, we need physical concepts, but we need also these appropriate mathematical tools. And then the question is, which language should we speak? Probably all of you or most of you are using classical mathematics, the mathematics you have learned in high school first and then at university. But this is only one possibility. And there is this Dutch mathematician, Brouwer, who is the father of intuitionism, and he introduced into his mathematics things which are very strange to us. The concept of an ideal mathematician, he called it the creating subject, who continuously produces new information by solving mathematical conjectures. Now, this is not very attractive to a physicist to think that there is someone or some mathematicians, even if it's an ideal one, that produces new information. But we know that nature, at least the quantum physicists know that nature is able to create new information. So maybe it is nature who is producing this new information kind of continuously. So I will present intuitionism without this ideal mathematician and motivated more by physics, particular physical concept of indeterminism. So maybe I should just warn you that Brouwer himself would probably not have liked my presentations because I'm just a physicist and maybe a naive realist, while Brouwer was quite an idealist from the philosophical point of view. And so my main claim is that intuitionistic mathematics is really the natural mathematical tool to describe indeterminism in physics, somewhat similar that derivative is a natural tool to describe velocity. So let's start basic mathematics. It starts with numbers, and numbers, if I ask you what are numbers good for, well, they are there to compute. That would be a natural suggestion. However, how can it then be that most of the so-called real numbers are not computable? They cannot be computed, not even with the help of any algorithm. So let's define some integers. Let's make it very simple. And you'll see it's even only bits that I'm going to define. So the first bit, n1, is defined as follows. So n1 equals 0 if every even integer between 4 and 10 to the 4 is the sum of 2 primes. And n1 is equal to 1 otherwise. Okay, probably many or most of you don't know the value of n1, but we all know that we could just spend a bit of time on our computer and just check whether n1 is equal to 0 or n1 is equal to 1. So no doubt n1 is either 0 or 1, and we don't know it, but it would be easy to find out. Second, n2 equals 0 if every even integer between 4 and 10 to the 100 is the sum of 2 primes. So again, no one knows the value of n2, but n2 can be computed, and very importantly, it can be computed in a finite time. Maybe this finite time is longer than a human lifetime, but it's a finite time. Or maybe it's a kind of Manhattan project to compute n2, but it's something we can do in a finite time, at least in principle. Probably no one is ever going to do that, but it can be done in principle. So probably we would agree that n2 has a value. It's either 0 or it is 1. Let's now come to n3. It's the last one. n3 equals 0 if every integer, even integer larger than 4 is the sum of 2 primes. This is Kullbach's conjecture. It's an old conjecture, a long-standing conjecture in number theory, but no one knows. And not only no one knows, but there is no algorithm or procedure which can guarantee to get the value of n3 in a finite time. You may try and possibly you may succeed, but you cannot be certain to succeed. So there is no known finite method to compute n3. So now what is the value of n3? Well, you don't know, I don't know. But nevertheless, every student knows that in order not to fail an exam, he has to claim that n3 has a determined value. No, that's probably what we would all say, because we have all passed these exams. We are all physicists or maybe mathematicians or related. And so we know that N3 must have a value because either Goldbach conjecture is correct or it is incorrect. Well, wait. If the exam is in intuitionistic mathematics, then the student should answer that the value of N3 of this bit is indeterminate, and that the law of the excluded middle is not valid. So here I'm starting to tell you about this intuitionistic mathematics, which is now way over 100 years old and still under development, and people, not many, but some mathematicians work on that. And you see, one thing which is now becoming really interesting is that there exist numbers, including numbers that are easy to define, that have a value which is indeterminate, something we don't encounter in standard mathematics. Standard mathematics, a number has always a value. And also here we start to see that the law of the excluded middle is not valid. So for instance, proving that N3 is not 0 is not the same as proving that N3 is equal to 1. There is something more here. There is then something more that comes in intuitionistic mathematics, namely the fact that these numbers, like N3, may evolve over time. Because maybe in 10 years, or sometimes in the future, someone will prove or disprove this Goldbach conjecture. And then, if it is proven, for instance, then the value of N3 will definitively become equal to 0. So today it is indeterminate, but in the future, that may change. It may change from indeterminate to a determinate value, for instance, N3 equals 0. So this is very counterintuitive to everyone who passed its exams in classical mathematics. But there's nothing logically wrong with this kind of intuitionistic mathematics. Let's go more into that. First, maybe quoting a few people. So here I'm quoting Karl Posse, who is a specialist of in intuitionistic mathematics in Jerusalem. Yes?
Can you ask questions, or you prefer to let it for me?
Depends how many questions. It's good to have a bit of questions, because then I realize that there is someone at the other end of the line, which is always the problem with Zoom. So tell me.
Okay. So, I mean, I was just wondering, so I understand mathematics is a language, but it's a very particular language that we look for some logical consistencies, no?
Yeah.
So the idea that we're saying is that the fact that someone really proves or not prove a theorem from some 10 years ago is not just going to change our knowledge of the language, but it's going to change the language itself. Is that, I mean,
No, it doesn't change the language. It's going to change the value of some propositions. For instance, a proposition N3 equals 0 is a proposition which today is indeterminate, but in the future could become determinate. But maybe I should really I'm going to introduce intuitionistic mathematics in a more formal way in a few slides, and maybe hopefully you will understand it better. But maybe I can already say that, of course, with intuitionistic mathematics, you can do logic. It's not exactly the same logic as the one we're used to. Particularly, the law of the excluded middle is not valid in intuitionistic mathematics, but it's a consistent logic. And there are many things, everything we do in physics, you can do with intuitionistic mathematics. Of course, I'll also tell you something that cannot be done, but not in physics, but in classical mathematics, where the law of the excluded middle holds. Okay?
Okay, perfect.
Okay, good, thank you. So what Karl Posse wrote is the following. We humans have finite memories, finite attention spans, and finite lives. So we can fully grasp only finitely many finite-sized pieces of a compound thing. There is no infinite helicopter allowing us to survey the whole terrain or to tell how things will look at the end of time. So you cannot look ahead. You look at what you have now, which is finite. Another important mathematician in this case, Eret Bishop, wrote that classicists, or people working in classical mathematics, wishes to describe God's mathematics. The constructivist to describe the mathematics of finite beings, man's mathematics for short. Constructive mathematics does not postulate a pre-existing universe with objects lying around waiting to be collected and grouped into sets like shells on a beach. So Bishop was especially a constructivist. He had also interest in intuitionism, which is a subcategory of constructivist. And Brouwer, so the father of intuitionism, he wrote, nature simply has not yet fully determined all objects. And again, if you are a quantum physicist, this sounds very familiar. No, it's like a bit this uncertainty or indeterminacy principle by Heisenberg. And we know that, for instance, position of particles may not yet be fully determined. So that's really the essence of intuitionism. But I see, and I could already hear that some of you get worried. How could there be things, including even mathematical objects, not fully determined? And here, maybe to calm your worries a bit, let me really immediately state that with intuitionistic mathematics, you can compute and prove theorems, maybe not always the same theorems. I will give examples of in classical mathematics, or maybe also theorems that follow a different proof structure. But for sure, everything one can do on a classical computer can be done with intuitionistic mathematics. Indeed, if you think a classical computer is finite, it can be huge, but it's finite. And so everything you can put in a classical computer is finite information. And then you process this finite information over a finite time. And so everything you can do on a classical computer, you can do in intuitionistic mathematics. So if you believe that all physics can be simulated on a classical computer, you can do all physics with intuitionistic mathematics. And indeed, let's look at how physicists really, the real applied physicists do it. For instance, a very timely subject today is climate physics. So climate physicists, they make predictions about the climate and they put a lot of data into their computers, but they cannot put more than a finite number of data into these huge computers. And then they run their simulation over the next years or centuries to predict how things may go depending on our behaviors. And at some point, because this is a chaotic system, the climate is chaotic, so they will run out of information. So they will need, if you want, digits that they could not put as initial condition in their simulation. And so the way they do it, they use stochastic remainder. They just add random additional digits. And this may look a bit strange, or maybe some get worried, but if you think a bit, there is just no alternative. And anyway, these very, very small digits, they could not measure it anyway. So they are de facto random or stochastic. And clearly also a climate physicist, we don't compute the trajectory of a rocket. We are making probabilistic predictions. And these probabilistic predictions are serious, are reliable, but we need to use these stochastic methods. There is no alternative. And so somehow we'll see that these climate physicists, they are using intuitionistic mathematics. Okay, let's come back to here. We have already seen that, and you all know that this is usually considered as deterministic. Is that really so, or is it the consequence of the language? So assuming this God eyes of you, a view from the end of time. And so here, again, a philosopher from Jerusalem wrote, tense and passage of time are not and never were and probably cannot be part of physics and its language, because he was thinking mostly of classical mathematics. So let's take now a very simple example of a chaotic system, hoping that this will make everything a bit more clear. So here I have just a one-dimensional state space. This is just the probability of rain. So 1, for sure it rains, 0, it's very sunny. And now the time evolution, and I will use the well-known Baker's map. So you stretch that by a factor of 2, and when you fold it back, so mathematically it's this. But if you write it in binary format, so this is a number between 0 and 1, so it's 0 dot, and then you have a string of bits. So this transformation, this Baker map, corresponds just to drop the first bit. The second one now becomes the first one. The third one becomes the second one. So they all shift by 1 to the left at each time step. And now, obviously, whether x, or this probability, could have been a p here, lies on the left half or the right half, so whether it is mostly sunny or rainy, after n time steps, depends on the nth bit of the initial condition. And now the real question is this billionth, if the billionth or millionth bit physically real? So the question is not whether this billionth bit can be measured. Obviously, it cannot be measured, but whether it corresponds to something physical. So let's look a bit more about real numbers. So real numbers, all the ones that one encounters, are actually exceptional. They are exceptional already because they have a name, and they are defined by an algorithm, like square root of 2, pi, fractions, and so on. However, the bits of a typical real number, so these bits of the typical real number, they have no structure whatsoever. These bits are random, totally random, or random or quantum measurement outcomes. So you start seeing, I mean, when we use real numbers, what we're actually using or postulating is randomness. And actually, a good way to think of a typical real number is really just what comes out of a quantum random number generator or any true random number generator. So these bits that come out that are produced, for instance, by this quantum experiment, this is a typical real number. Since there are only infinitely but countably many names and algorithms, a typical real number, you know that there are continuously infinitely many real numbers, has to contain infinite amounts of information. And for instance, the fact that you need this infinite amount of information, Émile Borel, the well-known mathematician, illustrated that by the remark that in one real number, so one single real number, one can actually code the answers to all questions one can formulate in any human language. You know, these bits could be just the answers to all possible questions which are ordered, let's say, in some which get ordered in an appropriate way, lexicographic way. And Gregory Chatin, who is really a master in complexity theory, he said that not only is this a good way of thinking of a typical real number, he said this is the only good way of thinking of a typical real number. So typical real numbers, maybe initially they have some structure, that's what you see and understand and master, but this is finite. And everything that comes afterwards has to be total randomness. So when we say, for instance, that x0 be a real number, for instance, coding the initial condition of some chaotic system, what we are effectively saying is let x0 denote an infinite amount of information. So initial conditions are not innocent. And let me here introduce an assumption, and you buy the assumption or not, but I think it's a very natural assumption, but I admit it's an assumption. The assumption is just that in a finite volume of space, you cannot code more than a finite amount of information. So if you have this little volume of space, let's say a centimeter cube, inside you cannot have more than a finite information. Here. And so if I put now a marble, a little ball inside, the position of that classical particle, center of mass, let's say, is not a real number, or at least it cannot be a typical real number. And some people may say, oh yes, this is Bekenstein bounds. Okay, maybe you don't know, but yes, it can be derived from that, but I don't think you need to understand quantum field theory and black hole physics to understand this assumption. So it's a natural assumption. And with this assumption, you can really conclude that, well, real numbers, typical real numbers at least, are not physically real. So here is an example of a typical real number. More precisely, this is my intuition of a typical real number. So it starts in this example with a 0. Okay, it could be any integer here, doesn't matter. Then comes the dot. And then you see where all these digits coming one after the other. And it continues. It's a unlimited sequence. So it goes on, it goes on. And you understand that if I wait long enough, at some point, the screen will be full. But then it continues. Now it continues below and it continues. So I'm in Switzerland. At some point, it will cross the earth and maybe come to Brazil. Okay, you're not exactly opposite to Switzerland, but anyway, you know, and then anyway, it will continue. It will go out of the solar system. It will get out of the galaxy and it will never stop. It's going on forever. So this is probably a way of many of us thinking about real numbers. But this is not the way mathematicians, the classical mathematicians, think of a typical real number. Let me show you how a classical mathematician think of a typical real number. So just watch your screen very carefully. Careful now. Infinite information in 0 time. That's a typical real number for classical mathematics. Everything at once. 0 time, infinite information. Wow, beautiful. But is that physical? So here we see, and we start also understanding that here, instead of indeterministic events, these digits coming one after the other, happening as time passes, all the indeterminism is coded in the initial condition. Everything at t equals 0 at the Big Bang, let's say. So instead of God playing dice as time passes, God played all the dice at the Big Bang and coded all outcomes in the initial condition. This is actually the physics that we learn at school and universities in classical physics and in relativity. But so it seems really that it is the mathematical language that forces us to speak of deterministic chaos. If we move to intuitionism, then chaotic systems will no longer be deterministic. So mathematical real numbers are not physically real. So often I like to say just mathematical real numbers are not really real. That's what I have here. Real numbers are not really real. Again, this helicopter doesn't exist. The climate physicist we already saw. And it also will mean, and I give examples more precise about this lack of the law of the excluded middle. So we already understand now that whether Newtonian classical mechanics is deterministic or not is not a scientific question. It actually depends on the physical significance when associates with mathematical real numbers. So it depends on this language. Okay, so we all know about this encounter, this magical encounters about 100 years ago between Einstein and Bohr, as you see here. There was also another one in Paris between Einstein and Bergson. Bergson was very famous, a super famous philosopher at that time, probably the greatest philosopher at that time, a specialist in time. And of course, Einstein was also the physicist, one could say, specialized in time, in physical time. And as you know, Einstein claimed, first of all, God does not play dice. And secondly, there is no such thing as the philosopher's time. Now let's revisit these using now as main character David Hilbert, the very well-known mathematicians, and Brouwer. So on the Hilbert side, I take Hilbert as the figure of classical mathematics. So here, every real number is an individual, completed, everything is already there, entity. All digits are given at once. And the continuum is a collection of individual points. So somehow here real numbers exist outside of time in some ideal Platonistic world. Of course, if you use this kind of mathematics, it will be difficult to tell stories about the passage of time because there is no time here. On the other side, on Brouwer's side, the father of intuitionistic mathematics, so for him or for intuitionistic mathematics, real numbers are processes that develop in time. I'll illustrate that shortly. And here, so digits are not all given at once, except for computable numbers, because there is a finite algorithm. And the continuum is a viscous collection of processes. I'll explain viscous collection shortly. So here in intuitionistic mathematics, time is essential. At any instance, only finite information exists. So let me now define intuitionistic mathematics. So Brouwer, he introduced the terminology of choice sequences, alpha of n being time instances. And for Brouwer, these choices were made by these idealist mathematicians. But I don't want any ideal or idealized mathematician. So I'm making the assumption that nature has the power to produce true randomness, to produce new information. So I have this natural random process, which produces, let's say, random bits. Let's make it simple, just bits, one bit at a time. And then with these, I'm going to define these choice sequences. So the choice sequences are defined as follows. So at each time step, the natural random process outputs some random number, r of n. And the next element of this choice sequence, alpha of n, is a computable function of the previous value of the time at which all that happens, and a function of all the existing information. So this is the information that this natural random process has produced, but of course it's not a function of the future. And we also make some assumption about convergence, which Brouwer also had. Okay, so let's now come to some examples of intuitionistic numbers. So the first example is the one that you have essentially already seen. So the next element in this choice sequence is the previous one, to which you add one more bit, and the bit you add is what comes out of this random number generator, this natural random process. So it's this Bn here. But you see, it stops here. There are no dots here. So at finite time, it's a finite number, finite information. A second example of intuitionistic numbers is a computable number. So all the numbers you can name, they all come here in. And so you may think, for instance, of a pseudo-random series, where here we take only k of these random bits, which act as a seed for this pseudo-random sequence. So this is an example. Of course, there are many more, and the typical computable number is pi, the ratio of, you know what pi is. And so this one, the bits of a computable number, they are all fully determined by an algorithm. So here you have an example of an algorithm. And of course, it will take time to run the algorithm, but it's a finite time in the sense that every bit can be computed in a finite time. And the bits may look random, but actually they are not random. They are all hidden in the algorithm. And for example, something which I think is very illuminating in this specific algorithm that computes pi, one can compute the nth hexadecimal of pi, and hence also any bit of pi, without computing the previous ones. So you can compute the first ones, you recognize these ones, and then you can jump, let's say, 1,000,000 steps ahead and just compute the bits 1,000,000, 1,000,001, and so on and so on. And the fact that you can jump ahead really illustrates that the bits of pi don't come one after the other. It's not like my example of a real number, at least my intuition of a real number. Here you can jump ahead. And that really shows that they are all already there. They are all already in the algorithm. Let me come back to a more typical intuitionistic number, which I call finite information quantity. By the way, all the names I gave to these intuitionistic numbers are my inventions, are my names. So here you again have these outcomes of the natural random process, and you take a finite number, here in this case k of them, and then you don't just vote the majority, you know. So you look whether you have a majority of zeros or a majority of one. And then if you do that, you will have some bits that are already fully determined, because that belongs to the past. If you go far into the future, this is still totally undetermined. And in between, you may have a transition over this length of k, because indeed, it might be such that the previous bits are already biased towards 0 or biased towards 1. So with almost a majority of 0 or almost a majority of 1. And so the probability here in between, or these propensities, as I like to call them here, they might be not 0 and not 1. They might be any fraction in between. Okay, and here are some examples, but I think we understand what a majority is, so I don't need to go on. And come to this very important fourth example of intuitionistic numbers, which I call mortal number. So these are numbers, so 1/2 plus or minus, and whether it's plus or minus depends whether Rn is 0 or 1, of a very small number decreasing. So you have an alpha of n, this choice sequence is fluctuating around 1/2, sometimes a bit above, sometimes slightly below. And this choice sequence goes on fluctuating until, by chance, the last half random bits all happen to have the same value. And let's say n is large enough and even so that you have a majority. Good, so you can do that. And then if by chance this happens, that half of the last bits are all equal, means all equal to 1 or all equal to 0, then the series terminates, the choice sequence terminates, so dies. That's why I call them mortal number. And then it doesn't move any longer, it sticks to where it is. And because the probability of termination decreases exponentially, you need by chance to have this larger and larger sequence of n/2 random bits to be equal, that implies that there is an a priori probability that the sequence, the choice sequence, goes on forever. So you have a situation where you have this fluctuation just around 1/2 until by chance it stops above or it stops below. And so clearly in this case, the proposition alpha smaller than 1/2 is neither true nor false, but indeterminate. It becomes determinate when the choice sequence dies. Here, a last example. This is an example I call autonomous number, because here the function does not depend on the time instance n. It is okay, this equation here, and you see that this part here will be 0, so it will be constant if alpha n is equal to 0 or equal to 1. So these are fixed points. And if you look at that a bit, you will see that this alpha n converges to 0 or to 1 with these probabilities. You know, and this now starts really to smell a bit also quantum, where we know that, you know, the wave function at some point collapses to 1 or something else, so one outcome or the other, with some probabilities given by this, okay, probability amplitudes in this case. And indeed, if you look at, and a bit familiar maybe with stochastic Schrödinger equation, like in the GRW model or the quantum state diffusion model, similar, very essentially identical stochastic equations, stochastic Schrödinger equations, and if you apply it to a superposition of all the photon numbers, so 1, 3, 5, 7, and 9, you get here just a certain number of solutions, stochastic, but you see that they all converge to an eigenstate of photon number, and we will do it with the appropriate quantum probabilities. And if you go more into that, and I'm not going to present that here, but believe me, this is essentially this type of equations. where mu is actually a parameter driving how fast the collapse happens here. So interesting here, we see that intuitionism brings classical mechanics closer to quantum. I like that very much, because people working on quantum foundations, they almost always, since now almost a century, not quite, but getting close to, try to bring quantum closer to classical. And I think a good idea is to try to do the opposite, namely to bring classical closer to quantum. Okay, so time is essential. I have already said that. And obviously, for instance, a statement like R at time n in the future equals 0, this statement or this proposition is indeterminate before the nth time step. As I already said, alpha smaller than 1/2 is indeterminate. And I like to put it in parallel with the more physical claim or proposition. It will rain in exactly 1 year from now at Piccadilly Circus. Now you may say, oh yes, I don't know whether it will rain, but for sure it is determined. Well, for sure, if you have passed all your classical mathematics exams. But if you think a bit, why not imagine that the future is open and there is no physical fact that forces you to accept the idea that this proposition has a truth value? Maybe the real truth value of this proposition is just indeterminate. Not only do we not know, but also nature doesn't know. It is really open. And so we see that the law of the excluded middle is not valid. I have already alluded to that. And this is certainly surprising because it implies that no non-constructive existence proof will exist. Now, again, mathematicians use, and they are quite successful in using non-constructive existence proof. But notice that in physics, we never need non-constructive existence proof. We need, on the contrary, constructive existence proof. If not, well, can always make nice claims, but if you cannot sustain them, it's not useful. At least it's not physical. So I think this absence of the law of the excluded middle in the logic of intuitionistic mathematics is surprising. I admit that, of course, but I think it makes plenty of sense in an indeterministic world, a world in which the future is open. Now, as Prof said, the excluded middle fails because the world is not yet determined. So truth about it are indeterminate. So let's talk about the continuum. So the continuum in intuitionistic mathematics are evolving sequences of computable numbers. So you get from one to the other these choice sequences. Very important, there will not be any hole. I mean, every element in this continuum is part of the intuitionistic continuum. There are no holes. However, because they are numbers that you never know whether they are smaller or larger than 1/2, like this mortal number, which is fluctuating around 1/2, it will be impossible to cut the continuum into those numbers that are smaller and those numbers that are larger than 1/2. You cannot cut them, or you cannot pick out one number from the continuum, one intuitionistic number out of the continuum. And that leads to a very important theorem, which is only valid in intuitionistic mathematics, not in classical mathematics, that states that all total functions, so functions defined everywhere, are continuous. You don't have step functions, but obviously you don't need a step function in physics. We need functions that can transit very quickly. And this is the meaning of viscous. You cannot take out one intuitionistic number, not more than you can take out a molecule of honey out of a honey pot. Okay, so some more, maybe I should just accelerate a bit here. You can also add, of course, choice sequences. You can compute any computable function like a sinus of these choice sequences. You can define order, which actually is only a partial order, because again, you don't know whether it's larger or smaller than 1/2 in this typical example. So this is a partial order. You can also define new concepts like being apart, which means that two intuitionistic numbers are apart. If you can really put your finger in between them, there's really a place, a hole in between them, and so on. So I want here to emphasize how much connections I see between indeterministic physics on one side and intuitionistic mathematics. You know, if you believe in indeterministic physics, you would certainly agree that the past, present, and future are not all given at once. But that's exactly described in this intuitionistic mathematics by digits of real numbers not being all given at once. Time passes, number are processes, indeterminism, numbers contain finite information. The present is thick, no time to really develop that, but the continuum is viscous. The future is open, no law of the excluded middle, becoming, choice sequences, and experiencing intuitionism. I'm getting very close to the end. Yes, I think I should soon. But let me just illustrate how the stories we tell change with this view of intuitionistic mathematics or indeterminism in physics. So Sabine Hossenfelder is a quite well-known high-energy physicist, and also now turning more and more into foundations of quantum mechanics and so on. And she has a very nice series of videos on YouTube. And in one of them, she says the following: "You are here to hear what science says." Looks very good. "Initial conditions determine all events, including chaotic systems. The entire story of the universe was already determined at the Big Bang. We are just watching it playing out." But she continues, "We know the future is determined by the present." And she even asserts, if you think otherwise, you are denying scientific evidence. Now, obviously, if you listen to me until here, you have understood that she is deeply mistaken. She is confusing science and mathematics. Of course, she's not the only one. You have many books and other authors that confuse here things. Indeed, I mean, here the picture that Sabine is presenting to us is really like, you know, everything is already in the movie. And we are just watching it playing out. But if we watch a movie, we know that sometimes the movie is exciting, is funny, or maybe is boring, whatever. And so we feel the time passing. However, you know, it's not that time is passing in the movie. The time is passing in the spectator. But if now we're talking about the entire universe, of course, there is no we that is watching it. Okay, indeterminism in physics. Once you have that, you can react in different ways. One possibility is to search for supplementary variables or to accept rest potentials. Let me go quickly about that. So here, supplementary variables, I will just go a bit quickly. I have already said, maybe here I have to say. So postulating that the initial condition of classical dynamical systems, including chaotic ones, are faithfully described of mathematical real numbers, classical mathematics, is certainly an elegant way of adding all future results while making sure that they remain inaccessible for long enough a time. So essentially, what we conclude from what I have said so far is that the real numbers, so the classical real numbers, they are actually the hidden and clearly inaccessible variables of classical mechanics. And I think this is really an important conclusion. You know, people were usually looking at hidden variables for quantum mechanics without realizing that actually the hidden variables, they are not only, okay, they're not in quantum mechanics, at least not local hidden variables, but in classical mechanics, they are using hidden variables all the time. And the fact is that almost all physicists accept real numbers without noticing that they are hidden variables, while the same physicists usually reject Bohmian positions as unnecessary. Okay, of course, you need now to know what Bohmian positions are, but here I'm referring to Bohm's mechanics with non-local hidden variable. Okay, let's come to this second aspect, the rest potential. So now we are talking about indeterminism. So a causal chain that starts from nowhere is magical. And that's probably the reason why so many people, physicists and philosophers, have difficulties with indeterminism, because indeterminism may give the impression that something starts out of the blue, out of nowhere, and that's magical. It's not physical. But on the other side, that a physical system has a state that is not yet fully determined is physical. I mean, certainly every quantum physicist has that all the time, but also just our world is indeed full of indeterminacy. And now as time passes, new information reduces this indeterminacy. So it's not information, new information of a human being or of an animal or of God or whatever. It's just new information that gets created by this power that nature has. And by making this indeterminacy reduced, then a chaotic system may evolve rather in one direction or in the other direction because of this additional information, or these additional digits that supplement the given initial condition. And so this indeterminacy does not come out of the blue. It is not acausal. Simply some potentialities get excluded. Okay, and with that, I come to my conclusion. So I already said mathematical language is important. With classical mathematics, classical mechanics is deterministic, but with intuitionistic mathematics, it is indeterministic. The classical real numbers are the hidden variable of classical mechanics. And so somehow with classical mathematics, you assume a view from the end of time, when everything is already done, where all the information is there. And then, of course, from the end of time, seen from the end of time, everything is there. There is no future any longer, and then everything is determined. Intuitionism brings classical closer to quantum. Okay, I had no time to talk about relativity. So indeterminism is physical. As time passes, indeterminacy is reduced, and some potentialities get excluded. So thank you very much. I hope we still have some people who are online, and I'm certainly willing to answer some questions if there are some.
Okay, thank you, Nicolas, for the talk. We certainly have a lot of people online, and I guess we had some questions. So yeah, we're open for questions here on Zoom and also on YouTube. You can write your questions and I will bring it over here. So I think there was a question in the chat by Daniel. Probably he wants to ask himself.
Let me see. I don't see my chat now.
I can ask directly.
Yeah, even better.
Hello. So you said early on, you said, oh, you're a realist. I'm wondering what that means with these intuitionist numbers, because it would seem that the value of a number is then subjective. Because
No.
But let's say a man in a desert island proves Goldbach's conjecture and doesn't tell anyone. So that N3 in the beginning is 0 for him, but it's still indeterminate for everyone else. So do numbers depend on who's talking and when?
So if we follow the old idea by Brouwer, I guess you're quite correct. I mean, someone could prove Goldbach's conjecture on his island, and it would change only for him. So this is not what I have in mind. So, and that's also probably why Brouwer would not have liked my way of presenting it. So for me, you have really nature producing information, but this information is not on an island or is not limited. It's just existing information now. Whether you know it or not is completely irrelevant. In this sense, it is objective, not subjective. And then these numbers would evolve would really evolve. And so I'm a realist, but I'm not a determinist. So for me, realism and determinism are two completely different and disjoint concepts. And for me, one can really take probabilities, and that's why I like to call them often propensities, or something being real. I mean, these propensities are real. they're not yet, the propensities are real and are determined, but the outcome of, let's say, the bit in 1,000 time steps is simply not yet determined, but it will be determined by nature, and it will not be determined for one person or for a few persons. It will just be like that. Maybe I can even show you these kind of pictures here. So if you have a random number generator here in this space-time diagram, so the idea is that here in the entire future, so in this light cone, future light cone, the bit is now determined. But everywhere else, so of course in the past it was not yet determined, that's obvious, if not that would not be a random number generator, but everywhere else it is still not determined. So it gets determined in this future light cone, but this completely independent of whether people pay attention, are interested in it, or that doesn't matter. Sorry. Yeah.
Okay, that clarified it.
Okay, thank you.
Any other questions? I have a few questions. First one, so I think, the only place where in physics that real numbers are really important and necessary is like when you're talking about the continuum of time and space, no? How is this related to consider that space and time is not continuous anymore, like some discretized notion of space? Is there any relation with these people that like to think of space and time as some discrete continuum?
Yeah, there is probably some connection, but most, if not all, people talking about is cellular automata or discretization, space and or time, they usually present that as a kind of fixed discretization, maybe involving Planck's length or Planck's time or things like that. While the view here is that this kind of discretization gets refined as time passes. You get this additional information which somehow makes your grid smaller and smaller. You get additional digits. But on the other side, if it's a chaotic system, the chaos at the same time stretches everything so that you more or less stay at the same level of discretization. But it's for sure important. It is not a fixed given discretization. It really depends on your system.
I see.
You only get the information which is necessary, and you don't get more than that.
Anybody? I want to give, and also, this analogy that you do with the hidden variables in quantum mechanics, I'm a bit confused because it seems in your idea we shouldn't. I didn't really understand what you mean by the real numbers are the hidden variables, because we shouldn't really look for them, no? Because it seems like nature is just creating them. Because it seems like in quantum mechanics, people are always looking at some hidden variables that it would allow you to predict things. But these hidden variables of classical mechanics that they're saying, they will not allow you to do that, no?
No, indeed. So in classical mechanics, well, think again of any chaotic system. Of course, you cannot measure the initial condition. We just postulate that this initial condition are faithfully described by classical real numbers. So we're postulating this infinite amount of information, all these digits. And then we say, oh, see, this is deterministic. But we have not proven that this is deterministic or deterministic chaos. We have just postulated that it is deterministic because it is only in the initial condition. But this is just a postulation. It is certainly not a consequence of any scientific fact. It is because we use this classical mathematics, while if we have the idea that these numbers come one after the other as time passes, then the same classical chaotic dynamical system would be indeterministic.
Anybody else?
Chuck, someone raised the hand.
Oh, please just go on and open your microphone and shout.
Okay, it was me. Hi.
Well, thanks a lot for the talk. And I guess like the obvious question, especially to you, is would then be possible to use classical physics to generate true random numbers, or would you still need like the quantum random number generators, right?
Yes, that's a good question. I think what is really missing to really use classical mechanics to produce true randomness is, you know, at what rates do these new information come out? How much randomness can you extract from a, let's say, a chaotic system, for instance? And here there is this clear difference in quantum. It is very clear you have these photons, let's say, hitting a beam splitter and then the two detectors. And so each time you get a click either on the left or on the right-hand side, with these two single photon detectors, you know you have a new bit. While in a classical, you cannot quantify it. And the difficulty or impossibility of quantifying how much new information you get makes it impractical to produce, let's say, certified randomness out of a classical random number generator. And this is also the case. You have commercial classical random number generator that, for instance, based on thermal fluctuations or things like that. And as long as it is purely thermal, you don't really know how much you can take out. And then usually what people do is that they take out quite little. I mean, the rate of this classical thermal random number generator is very low, much lower than what you can do with a quantum random number generator. But I would agree with you that the distance between quantum and classical is becoming smaller. Maybe there's another thing. In classical mechanics, so I'm clearly on the side of this indeterminism and so on, but I haven't proven to you that that classical mechanics is indeterministic. I have only proven that, let me come back here. Why is it no longer? Can you see that? Sorry. Yeah. So I have told you, if you use classical mathematics, then classical mechanics is deterministic. It's an option. But another option is, if you use intuitionistic mathematics, then classical mechanics is indeterministic. So you have a choice. And then you have to trust one of them. It's not that one is necessarily correct while the other one is necessarily wrong. You have a choice. What important is that you have a choice. It is not like Sabine Hossenfelder claiming that indeterminism, an indeterministic viewpoint would be against science. It is not against science. It is just a choice. Well, in quantum, did that at the very beginning, summarizing with this Bell inequality violation, you can really prove on the very, very general assumptions that you necessarily have randomness. So again, here you have on one side, you have a choice. On the other side, on the quantum side, you have no choice. It is random.
Thank you.
I have a few more questions, but I'm trying to wrap my head around them as I speak. So maybe they'll come out a bit confused. So the first question is really, so when we think about science and we use maths and we use using the maths we learn, I mean, there's lots of results in maths that we use that rely on the excluded middle and rely on things being either 0 or 1. And I mean, some numbers at least can be kind of take it as a given. That, I mean, there's some things that are indeterminate like that, but there are others that you've mentioned. There are categories of numbers that really are 0 or 1 and are not indeterminate. Like, let's say if you have a set with a finite number of elements, and then something is either in the set or it isn't, and you can be sure that one of those two things is true in that particular case, not in general, maybe. So some part of our logic will still have to rely on the excluded middle. Maybe you have to assume that it works in that case. So my question is, what breaks down in our whole edifice of, theoretical physics once you have all these theorems and proofs that we rely on this logical construction to use? Now it's not true anymore. can't be relied on.
So I think I understand your question. It's a legitimate one. But I think if I really would now insist that you give me an example where any physics results really rely on the law of the excluded middle, you will not be able to come out with. I will give you an example shortly, but you will probably understand. The reason why I believe you will never be able to come out with, and you're not the first one asking this question, but you will not, no one is able to come out with a real physical consequence that relies on the law of the excluded middle, is that this consequence would be something you cannot simulate on a computer. And so, you know, if we believe that all physics can be simulated on a computer, then clearly the law of the excluded middle is not a necessity. Now, when I had this discussion with other colleagues, they sometimes come up with the following example. If you have a Hilbert space of infinite dimension, and you have just a Hilbert space of infinite dimension, and you want an existence proof of a basis, orthonormal basis, let's say. The standard way of proving the existence of orthonormal basis for an arbitrary infinite dimensional Hilbert space relies indeed on the law of the excluded middle. However, when we do physics, we don't have just, infinite dimensional Hilbert spaces. We have one which is very specific, you know. For instance, the set of the vector space of square integrable functions. And as soon as we have an explicit Hilbert space, even of infinite dimensions, then we can not only prove the existence of a basis, but we can construct one. You know very well how to construct the basis of the usual Hilbert space, you know, the L2 of R, for instance, for one-dimensional square integrable functions. And so I think this is the case for all physics. It's only if we start to do physics which smells more and more like pure mathematics that we might sometimes like to use the law of the excluded middle, but it will never lead to any physical predictions because, again, a physical prediction you can do on a computer, and the law of the excluded middle, and then if it is on a computer, you don't need the law of the excluded middle.
Maybe you needed to prove theorems about physical systems or something like that.
Well, maybe about the existence of a solution of an equation. You may have a non-constructive proof that an equation has a solution. But this is not physics. This has more to do with the formalism of physics. If you want to make a prediction, you don't want the existence of a solution, you want a solution. You know, if I tell you this set of equations has a solution, but in a non-constructive way, how are you going to test that physically? You cannot go to a lab and test that these equations have a solution or not. So if you tell me this is the solution of this equation, then I can go to a lab and make a test. So it's only the constructive results that can be tested.
I have to wrap my head around that one. And one last question, if I can.
Sure.
So you say you're bringing classical mechanics closer to quantum. Are you secretly trying to make them the same? Is that the actual goal? I mean,
I think no. So I'm certainly looking how much of, you know, all this quantum strangeness is really quantum, and how much is actually not quantum. So, for instance, indeterminism, I don't think this is specifically quantum. Also, the reduction of the measurement problem is not specifically quantum. Even non-locality is not specifically quantum. However, the violation of Bell inequality is certainly specifically quantum because it requires incompatible measurements. Or if you want, it really requires that you have a minimum, well, you have these uncertainty relations, delta P, delta Q larger than H bar. And incompatible measurements, this is something which I don't think I can introduce into classical physics. I believe that's where the two theories are and will remain distinct.
Even if they're based on intuitionist mathematics.
that's my, okay, that's today. Okay, this is something that I have not written down. You see many of my papers here at the bottom of this slide. So I don't know yet, but I'm pretty sure that there will remain this difference. And I think that, you know, H bar enters in these uncertainty relations and or commutation relations. And this is what really makes quantum specific. You know, Bell inequality, H bar is hidden in it, but in just okay, that's now more complicated. You know, non-locality in the sense that, in the EPR sense, that you can do a measurement on one side that affects the determinacy on the other side. For instance, you measure position, and position on the other side also get reduced. This is something that you could also have classically.
So,
is
but
there
I
time
mean,
for
why
one?
would we? Oh, come on, you go ahead, Marco. Yeah.
Can I ask you a question? Well, thank you for the presentation. Those are very interesting and, you know, thought-provoking ideas. I'm like my colleague Daniel just mentioned, we're all trying to wrap our minds around them. It's all very new to me. And but I have one question, which is a difference between our understanding of nature and how nature behaves by itself. For example, I could imagine that like a computer could produce every single book that exists, like every 300-page book is by random characters, producing random characters. And most of those books would be complete bogus, but you know, some of them will be meaningful, and there will be some that, as far as we know, contain all the truth that we will one day get to. In a sense, like our minds are finite. Like we can only talk about finite things. That's how our minds work. We have certain limitations on our knowledge. So don't you think that there's a little bit of a division between these two things here? Like, for example, most numbers that we can talk about, not most numbers, all numbers we can talk about require a finite string of characters. And those we know are very limited set of numbers. So in a sense, most numbers we will not even be able to talk about in our lifetime, you know, forever. They're just hidden there, but we know they are there.
Well, we know. So, no, sorry. Let me just react. So, I agree with many things you've said. For instance, we are finite beings. I think I said that very explicitly. And indeed, the numbers we know, all the numbers that are accessible to humans, will all be computable numbers. And computable numbers, by definition, are those numbers for which you have an algorithm, a finite algorithm to produce them. So indeed, it has to be finite. But then you just at the end jump to a conclusion which I think has more to do with your education. Namely, we know that the other numbers are there. How do you know that they are there? They are postulated by classical mathematics, but you have no idea whether they're really there. And that's the main difference. If you really believe, but it's a matter of belief, that all these other numbers, so the non-computable numbers, they are there. And again, you have, like me, be trained during all our university years to believe in that. But so if you believe in that, then you believe in classical mathematics, and you will conclude that physics is deterministic, or at least classical physics is deterministic. But you don't have any solid fact that supports your belief in these other, so the non-computable numbers. And what intuitionism is telling you is that these other numbers, they don't exist yet, and they will never exist at any finite time. Of course, at the end of time, whatever that exactly means, you know, if you go to infinite future, then everything is there. But at any finite time, like now, these non-computable numbers do not exist. So that's maybe the answer to the last part of your question. And maybe also at the beginning, you said, oh, these random books or books typed by whatever, produced by a random number generator. A random number generator should be able to produce any book. And some of these books you said might be meaningful. That's probably not correct, because to make some books meaningful, you have to order these books and even find out, what is even the concept of a book. If you just have this infinite string of characters, maybe you can then arbitrarily decide to divide them in 300-page books. But even then you have, of course, an infinite number of books, and you have no way to even search for these books. So to say that a book has some meaning, I don't think it is very relevant.
Well, no, but I could say that, I'm using English and, some mathematical symbols, and, I'll ask a computer to just like analyze these books, and they see if it's in correct grammar, and, if mathematically the propositions follow logically from each other, and verify if they're correct or not.
Yeah, but they might be syntactically correct. That doesn't mean that they have a meaning. I don't think they are going to tell a story which is useful for humans. So I don't think just a random sequence can by chance, you may have suddenly a string of many zeros, or a string which reproduces today's news on a TV channel, but that doesn't mean there is any information in it.
No, sure.
There's still no information in that kind of random sequence.
No, perfect. I was not actually thinking of a random sequence, really. I was thinking of just like producing. We know it's a finite number of books. They're like, I don't know, each line has maybe 40 characters. So for each character, there's like maybe 30 choices, just 30 times 40 times 40 lines times 300 pages. It's a huge number, but it's a finite number of books. So,
yeah.
One of these books may be telling us the final story.
Yeah, but it's useless. It's probably correct, okay, but useless.
Okay, thank you.
You would need then the pointer that points you to the right book. Okay, anyway. Yeah, but I agree, it's a finite number. That is correct.
I have a quick question. So this would be, you said that you could even have no locality classically, but would be, the source of it would be this random generator.
No, okay. This, I was not really prepared to say all that, but you could have that Alice's system has some indeterminacy, Bob's system has some indeterminacy, but their relative distance, or some relation between them, has also some indeterminacy, but maybe smaller indeterminacy. And so now if I measure on one side, I will learn enough to reduce also the indeterminacy on the other side. This is really like we have also with entanglement, except now I'm talking only, let's say, entanglement in 1 degree of freedom, and we know that to have real quantum entanglement, we should have this indeterminacy, this relation between indeterminacies in several degrees of freedom, including in an incompatible one, like position and momentum, for instance.
But isn't the case that as time passes, the indeterminates they are having are decreasing, but they are decreasing by the same source? No, wouldn't be the source of correlation between?
Well, I'm not sure. I think you can really think that you have some initial indeterminacy on both sides, but the relation between the two has less indeterminacy than everyone has locally.
Okay.
So this is something that we have in quantum mechanics with position, for instance, or energy. And I think we can mimic that also in this in classical mechanics. Now, I'm not saying that nature is using that. In any way, nature at the end is quantum. But you can certainly have a classical model of this kind of non-locality, this form of non-locality. Again, not the one that violates Bell inequality, but the one I just mentioned. This, I think, can be mimicked using just classical mechanics. But this, again, is not, I'm not claiming, again, that classical mechanics is like that. I'm just saying that when you try to bring classical closer to quantum, we can go a long way. Once we have indeterminism and indeterminacy, we can also include that form of non-locality.
Okay, I think, I mean, we had a nice discussion. I mean, really. So I'd like to thank Nicolas again for taking your time to explain this for us. I mean, it's already late night in Geneva. So, I mean, so.
Yeah, 10:30. I think it's time for me to open a bottle of wine and have a glass of wine
Sure.
before going sleeping. Well, for you, what time is it
Yeah.
for you now? You still have plenty of time, no?
It is still 5:30. Yeah, we still are having
Okay.
the sunset. Time for a beer here. Yeah.
Okay,
Okay.
very good.
So thank you a lot, and I mean, hope to see new achievements on these new ideas. They're very exciting for me. I think it's very nice, and I mean, new possibilities are always good thing in science. No, I mean.
Okay, excellent. Thank you very much for the opportunity to present my strange ideas to the Brazilian physics community.
Okay.
Okay.
Thank you, and thank everyone that they were participating. Okay. Bye-bye,
Okay.
Nikolai.